third panelist is Professor Bane Vasic. He's a professor of electrical engineering, computer engineering, and mathematics at the University of Arizona, and director of the Error Correction Laboratory. I guess I'll keep the introductions short, and please, you can say more if I've omitted something. But I just want to mention that he's done pioneering work on structured low density parity check error correcting codes, and these have enabled low complexity decoder implementations. So thank you and welcome. And then our last panelist is Dr. Ted Yoder, and so he received his PhD from MIT in 2018. He's been a research staff member at IBM since then. His interests are in quantum algorithms and also in quantum error correction, with a focus on new codes and architectural considerations. So welcome, Ted.
Yeah. Hi, everyone.
All right. Well, so I mean, I have a few questions just to kind of start the discussion. Maybe I can ask each of you a question, and then we can open up to things to more broad discussion. Maybe let me start by asking. Why don't I ask you a question, Ciaran? So in recent years, we've seen larger and more capable quantum systems, and they're beginning to be able to execute the operations that we need to demonstrate quantum error correction. And you've been involved in this research recently. So I'm wondering, so maybe you can tell us a bit about some of those results, but then also more broadly, I wonder if the panel, if you and the panel can talk about what you think it means to make an experimental demonstration of logical qubits. What criteria should those experiments satisfy, or what sort of steps along the way are going to be significant milestones?
Okay, sure. Yeah, so the research that we've been doing at Quantinuum involved we initially studied the Steam code. We want to kind of progress and push what you can do in experimental quantum error correction. So we, for the first time, we implemented repeated quantum error correction cycles. So there's multiple syndrome extraction rounds per QEC cycle, and being able to do real-time decoding after each cycle as well. And then after that, we also looked at two logical qubits. First was with the 5-qubit code using peaceable fault tolerance that Ted Yoder and others came up with, and as well as looking at two Steam codes and doing a transversal gate between them. And for the Steam codes, we start to see, not with necessarily QEC cycle, but as long as you fault tolerant encode and fault tolerantly apply the 2-qubit gate, we saw that we were able to prepare better Bell states than we could do physically. So we're starting to see little glimmers of being below pseudo threshold. Of course, you need to do more complicated experiments involving QEC cycles and chaining these things together to do logical algorithms. And there's also been not just our work, but other works the people like Ken Brown and others have looked at the Bacon Shore code and other codes. Rainer Blott has looked at also at the Steam code. Back in I think 2014, they're able to create a logical qubit and do some syndrome extraction. So in general, I think people sometimes ask, what does it when do you demonstrate a logical qubit? I think people have already demonstrated logical qubits. They've been logical qubits are basically like physical qubits, except that they're using other qubits. They are qubits. So you might have crappier worse logical qubits than physical qubits, but probably what people are more interested in is when you start to be in the regime of beneficial quantum error correction. So for those, I think there's probably a series of milestones, and those mainly involve first seeing that you're able to do, string these logical operations together and produce, enable deeper and deeper algorithms that perform better with better fidelities than you can physically on the same device. And of course, eventually, getting well below threshold or pseudo threshold, you don't want to sit at that because there's no point. You're just using a lot of resources to do nothing in particular. But yeah, so seeing that you can actually push well below pseudo threshold and start to get 10 to the minus 5, 10 to the minus 6, and so on, and then eventually building towards these tileable modules that everyone wants to do, as well as start interconnecting these modules together, and also maybe using certain modules to produce magic states and in enough abundance so that you're not limited by your magic state factories and so on. So these sort of series of milestones will, I don't know how long it'll take, maybe many years, but it's starting to be a pretty exciting field. We're starting to see real experimental QEC come about, which is really exciting.
So yeah, I wonder, the other panelists, please feel free to comment, but otherwise I can move on to another question. So I guess I have a question. Oh, please.
Yeah.
Go ahead if you'd like to say something.
Yeah, I think I agree with a lot of what Ciaran said there. But I also want to point out that there's like a huge parameter space here. There's, not only optimizing logical error rates, but just how many qubits are you using? How long does it take to do a logical gate? So all of these things, getting below certain practical values in all of these parameters could be significant milestones as well.
All right. Well, why don't I move on to the next question? I was curious to ask some of you who have. So I believe Robert and Bane have. You have experience with classical and quantum error correction. That and that experience is different than my own. I've been working in quantum computing for almost exclusively. I was curious, what are some of the, when you look at quantum technologies and you look at how classical technologies have evolved, if there are some key and important differences with regard to how errors are mitigated and corrected, as you see, maybe having to do with the dominant error mechanisms or the main challenges.
So maybe I'll start, and then Bane can correct me where I go wrong. I think that history of error correction is kind of interesting because it starts in the 50s and the 60s when there are no computers, and in a sense all people can do is mathematics. And so in the beginning, error correction was geometry, and the thing that you were trying to optimize was minimum distance. And in the late 80s, things changed. We started to be able to make computers that could implement algorithms, serious algorithms. And error correction changed character from block codes designed for distance to things like LDPC codes. So what changed was that instead of geometry being central, algorithms became central. And the interesting thing about LDPC codes is that, in a sense, the motivation for LDPC codes is that distance doesn't matter. As long as if you have a few low distance words, the probability that the noise takes you in the wrong direction is kind of small. So they don't matter. So it's always a little bit interesting for me to see LDPC papers in quantum where the objective is distance, because in the classical world, that's not what they were designed for. Anyway, I'll let Bane expand on that.
Yes, thank you, Rob. So you probably notice a lot of papers written recently about quantum LDPC codes, and it is, I guess, because some technologies allow non-local interaction of qubits and syndrome measurements. And in the morning, we heard from Misha Lukin about one platform to enable this. So this is what LDPC codes need. But then there is also the fact that LDPC codes were studied also in the context of fault tolerance in classical literature. So where logic gates that are used to implement decoders are, not as rich as in quantum. They are just XORs and majority logic, for example. You can use some other computations, but then you can show that that LDPC codes are actually can tolerate these errors. So now in the quantum setting, and of course the good thing about LDPC code is that they can provide a range of trade-offs. I mean, trade-offs between complexity, speed, overhead, hardware overhead, redundancy, etc. So, but now when you look lately, there were also some provable results. First of all, let me step back. When you try to make quantum LDPC codes, there is this symplectic product constraint that you need to impose, and the class of codes is less. So it was believed that minimum distance, as Rob said, that increases only as a square root of the length of the code. But it was proved that it is actually increasing linearly. So, okay, so we don't have to worry about minimum distance anymore. And some probable results actually show that the promise of LDPC code. So these are results that are very similar to classical results that use expanders, etc. So this is all asymptotically. But once when you have a I don't know, finite length code like 500 qubits or let's say 1,000 qubits, that some other effects will surface. And one of them is, of course, quantum people mostly are concerned very much with the threshold. And of course, this is very important, but when you increase reliability of qubits, another effect will show up, and it is the problem of convergence. So quantum codes, quantum LDPC codes use iterative decoding, and this iterative decoding can either converge or kind of get stuck. So now what we have been doing is studying these effects. And with Rob and Narayanan and Nitin, who are in the audience, we have this project where we combine like Reed-Miller codes that are protecting logic gates, but don't really necessarily have efficient decoding algorithm with LDPC codes that are more designed for memories, but have very efficient decoding algorithms. By the way, you probably, if you follow the literature, you also see that in kind of performance that we can achieve in classical LDPC codes are extremely low error rates, probability of error. So I design a code that is relatively long. I can run it and provide throughput of, let's say, 35 gigabytes per second of, corrected qubits. I can run it on FPGA or ASIC, and I can achieve probability of error of 10 to minus 17, for example, or 10 to minus 15. So these are things that we can demonstrate that we can do. If you look at the plots in papers for quantum, some of these algorithms have probability of error 10 to minus, 2 or 10 to minus 3. And this is at least, I guess, where my lab and this is what we try to do with Rob and Narayanan and Nitin try to improve, so that we still have very low complexity decoding algorithms, something that can run at extremely high speeds and still provide, significant boost in error performance.
I wonder, I'm sorry, please go ahead.
I was going to say, and that there's all sorts of things that work in the classical world that I'm not sure how they translate to the quantum world. Like in the classical world, there are these things called spatially coupled codes, which are low complexity. You think of low complexity LDPC codes chained together in an interesting way to produce a composite code that's far more reliable than the components. I mean, these kind of ideas that exist in the classical world, I think that they have potential in the quantum world too.
Yeah, so earlier this morning in the panel, people talk about collaboration between different communities, and I guess the purpose of this workshop is also to enhance this. So what we know now is that there are a lot of nice classical problems or nice solutions that our quantum physicist colleagues are not aware of. And we will organize some workshops and some special sessions at the conference, and we will invite more kind of quantum error correction physicists and classical error correction people. So for example, in LDPC codes, the good LDPC codes, these constructions are really based on classical codes. So you take typically two classical codes, and then you have to couple them to satisfy some constraints. And there are several constructions. So now, for example, a very interesting phenomena now happen. So, for example, for classical codes, we understand them very well. But when you couple them, then you create, all these codes are, as Rob said, decoded using some graphical models. So there are inference methods for graphical model. That it is what the decoder is. So now on one separate graph, on one classical code, they work in a way that we know. But when you group them together in this new graph, some new things happen, and these are not very well studied. So, for example, coupling these, additionally coupling these specially coupled classical codes, we can improve perhaps even more performance, or it can degrade it because of some unexpected phenomena. And it is worthwhile to investigate this.
This takes me in kind of two directions, but one, I guess one. One difference when we apply quantum error correcting codes in a fault-tolerant computer is that we need to apply gates to them. And this is very challenging on codes that encode multiple qubits. And so I was curious if if anybody would like to comment about potential approaches to do this. It may be possible to have architectures that allow these long-range interactions, but then we may be trading off space and time in a difficult way. Although the potential is there for dramatic resource reduction by encoding into larger blocks. I don't know if anyone would like to say a few words about that.
So, I mean, well, I'll say a few words. So I've always, as a coding theorist, been more interested in little codes that do cool things than in asymptotics. That's in a sense how I make my living. And so I think that, so I'm interested in CSS codes still. And I'm interested in the way that they interact with noise. I know that it's possible for certain noise models like coherent noise to design CSS codes on which the noise acts like the identity. And so one of the things that I'm very interested in is characterizing noise and then thinking about what kind of CSS, what kind of classical codes should be the components of a CSS code that doesn't feel that noise too much. Because at the back of my mind, I have this idea that physicists are the smartest people in the world and that they can make Hamiltonians. And what I hope is that we can make codes that fit with those Hamiltonians in interesting ways.
It's interesting that you point out the small codes. It seems like you know, people study both asymptotic fault tolerance and also you know, very concrete gadgets that we need to implement in the laboratory. And I'm curious so coming back to this question of minimum distance, if you're looking at small gadgets, you know, are we trying to optimize things like distance and stabilizer weight in a very concrete way, or are we looking for these very large, you know, families of codes that we can grow and implement a large computation that way?
By the way, I don't know the answer, a complete answer to this, but I can tell you what we know. First, how you create stabilizers. I make my living by taking codes, finite codes, and designing algorithms, simple design algorithms that can, I don't know, feed the budget, power budget, or energy budget, or complexity budget, I don't know, area budget on FPGAs or ASIC. So now we have a lot of flexibility actually to design codes using classical codes. And what we found that how stabilizers are created really influence the performance. So there is this concept that we recently introduced of a quantum trapping set. So this is configuration in the graph, in the structural stabilizers where error patterns that you are trying to find are kind of competing. So there are several candidates that are potentially error patterns. And since your decoding algorithm has this locality, it cannot choose between them. Then the second component of your question is, you know, we recently published this paper on where we compare and try to estimate really the latency and throughput constraints of different algorithms. So, you know, if we want to do error correction fast enough so that we are ready to accept next syndrome measurements without buffering or anything. Otherwise, things become complicated. So there were a lot of algorithms that are proposed in literature. You know, minimum weight, perfect matching. There is order statistics decoding. There is, you know, small set bit flipping decoding. So some of these algorithms are implemented for some classes of code. Some of these algorithms are shown to work asymptotically well, but are not really good for hardware implementation. However, these local algorithms that are based on you know, message passing are good candidates. They can meet these throughput requirements. So this is the second component. And the third component is about this interaction of, you know, protecting logical gates and error correction. So there is also you know, a new class of codes recently proposed called quantum tunnel codes that are not really designed for this purpose, but they could be modified to incorporate. So these are really generalized, what we call the generalized LDPC codes. So you can think of them or converting them into something that will have components codes that are Reed-Miller codes that are, let's say, that the small codes that Rob is talking about to protect, you know, qubits, and then have on top this kind of a larger code that will be very efficient to decode. But this is not done yet, so it is just a speculation.
And so this leads into another question, which is that there's interest in looking at modular and more interconnected architectures and making technologies that can realize these because of the potential to reduce overhead when you introduce some of these longer range connections. So I was wondering if you'd comment on the prospects for dramatically reducing the overhead, say, relative to the surface code or other architectures. I wonder, I don't know if Ted, you'd like to bring you into the discussion about gates and overhead.
Right. Yeah. So I thought it was nice that Rob brought up small codes that do interesting things, because if we look at implementing some of these good quantum LDPC codes asymptotically, the connectivity graphs they require are sort of infeasible, at least for like 2D planar architectures or something close to that, like we have at IBM. In fact, you need like an expander graph for your connectivity. So it would be nice if we don't go to the asymptotic, but we just look at some small codes that do interesting things and are maybe good enough to hit error rates that are practical. Maybe like 10 to the minus 12 or something is good enough for an algorithm that a classical computer can't simulate. Yeah, I don't know if I need to add anything more to this this comment, but yeah.
I don't know quite whether this is what you meant, but I mean, in the classical world, when you think about data storage, architects think about hierarchical locality. So if you're a computer architect, you want the typical case to run really fast. And so you design systems for storage where you might partition bigger Reed-Solomon matrices, and you might look at a piece of that, and maybe you have enough parity to decode what's there. Maybe you don't, but someone else can send you some parity. So I think that there are likely analogs in the classical world of that sort of way of organizing. Sorry, there are analogs in the quantum world of that sort of way of organizing in the classical world.
Yeah, that makes sense. So you might have, sort of dense connections locally, and this means you could use a very interesting small code that's concatenated inside a larger code that is overall less connected or something.
Yeah.
Yes,
See,
so
I must say, I love concatenated codes, and I actually feel that there still must be some juice in classical concatenated codes that we've looked at. There was this really interesting paper from German Aerospace Group where they said, "Oh, we'll just do this brain dead concatenation. Oh, look, it works really well." So I think that there's still some moments like that in front of us.
Yeah, that paper also caught my attention. The code also has a lot of symmetries that might be exploited for gates, which is also important.
Yeah, so also one thing that Rob said. So what Ted says about this kind of combination of locality and these small codes is kind of present in these generalized LDPC codes. So this could be pretty interesting to look. But also what Rob said about these typical cases for decoding, it is also most of the time your decoder converges in very small number of iterations, And it's so typically, couple of iterations, 1, 2, 3 iterations, sometimes 5. And then after if you don't converge, then you have to run some complicated algorithm. So you see, it is possible to kind of have concatenation of algorithms, so you kind of use general purpose algorithm for very low complexity and then switch to another a little bit stronger algorithm. So we call this diversity decoding. So where we kind of, search this space of errors. So we, so Narayanan and Nitin also thought about this idea of maybe distributed implementation of LDPC codes with with processor that are not one big processor, but some some error correction, but also kind of sharing sharing quantum information between different processors. So we have this paper on in the context of GHZ distillation, where different parties share entanglement and are trying to jointly kind of distill the entanglement by using LDPC coded LDPC coded information.
Yeah, just to elaborate on what Bane says, inside of your flash memory, when you just buy your computer, the algorithms are really simple because you don't have any errors. And then as your memory ages, they become more complicated. And the new algorithms kind of automatically trigger at certain points. I should also say, actually, something else that sometimes there are things that get under your skin, and you can't say they get under your skin because they're the most important thing in the world, but they still get under your skin. And one of the things that interests me about algorithms like belief propagation is the potential of unequal error protection. So, if you think about belief propagation, what happens is that you have these parity bits. And in the course of the algorithm, the information in those parity bits leaks into the message and you correct the message. And I'm sort of intrigued by making more reliable parity bits and thinking about what the potential advantages of that might be with respect to algorithms like belief propagation. I know that there are advantages in the classical world because I've implemented that idea in Flash, but I think that there might be advantages in the quantum world too.
Do you mean something like a kind of heterogeneous device?
Yes. Yes.
Okay. With specialized qubits, memories.
Exactly. So something to make the algorithm work faster and more reliably.
So, so a general question. When we look ahead, there's a need to chart a path from the systems that we have today to systems that are gradually more and more robust. It seems like this isn't something we can do in one giant leap by going somehow from non-fault tolerant to fault tolerant computers, but in some kinds of steps. And I was just curious to hear each of your perspectives about how we might achieve this.
So one of the things, let me give a shout out to your fellow panelist, Ken Brown. One of the in some sense, one of the great things about being at Duke is that we have this ion trap computer. You and IBM have this other computer. But what's magic for me is this idea that if we said, oh, maybe you should arrange your qubits in this way, and then the experimental guys can measure how reliable those qubits are. And, you know, I get excited about thinking that I could think of something just theoretic, and then I could see it in practice. I think those are the kind of steps you were talking about, and I think those are just magical.
Yeah, I mean, I guess another step is this merging of error mitigation and error correction, as we heard from Sergey. I think there's maybe more you can do there. For instance, well, I mean, the error mitigation seems to be useful for correcting cases where you don't want to deploy the full fault tolerance. Maybe it's too hard, it requires too many qubits. Like if you want to distill magic states, that might be too difficult for a small computer. So instead you apply error mitigation to it. So like maybe there are other examples of that, such as if you have a physical error model that doesn't match the theoretical error model that you designed your fault tolerant circuits for. So you have errors that are outside this like circuit poly depolarizing noise model. Can you correct those errors that you didn't account for using some error mitigation techniques, and then, you know, improve your error correction, your quantum code that way?
Yeah, this would be very interesting. I must admit that I'm not that familiar with the methods that Sergey presented, but they look very interesting, and I think it is worth exploring these connections. I guess we need to learn just more about, you know, these interactions.
Yes.
Yeah, merging error mitigation with like, you know, at the beginning we're already qubit constrained, and we're going to be qubit constrained for quite some time. We're not going to have a million qubits or a billion qubits overnight. So yeah, I mean, you probably have lower distance codes if you want to do more, deeper and deeper algorithms. So that's only going to reduce the error rates to some degree. So like leaking in some error mitigation makes sense. Also looking at like quantum error detection, like it might not be the thing that you want to do in the long run, but like, you know, quantum error detection requires a lot less resource overhead than full-blown quantum error correction. So that can be useful. And then just like, you know, just doing this stuff for real and learning what is the actual noise that really is the sticking point is important, because you want to not like optimize at the high level, you know, code level at first. You want to try to, as much as you can, optimize at the, you know, bare metal level and figure out what are the crucial errors, because some of the errors that we know about on the physical level might get washed out a bit on the logical level. So it's more important to see how they're working, you know, revealing themselves on the logical level. And then as we scale these things up, you know, some other, you know, bad crosstalk or noise that we don't like might, you know, appear. And so it's important to, yeah, just do these things and figure out how to fight them at the lowest levels, and maybe the algorithm, like circuit level, and then the algorithmic level, and so on.
Now, when you mention this, you see there are other things that the decoding algorithms can benefit a lot from. So one is some kind of a soft information about, or reliability information about, you know, let's say syndromes. You know, also taking into account this crosstalk, or, you know, this. So Nitin has shown that in concatenation with GKP states, these LDPC codes that can get some access to soft information can improve things, the performance a lot. So I think this is also a direction to explore. Also, sometimes in some cases, I mean, there are codes that are designed for erasures or combination of errors and erasures. So also having a mechanism and understanding of noise and kind of a way to declare what is an erasure can also help a lot, decoding algorithms and quantum codes.
Yeah, this is really getting at like the co-design aspect of this workshop, right? That the fact that you're using all the information you can from the hardware and feeding that into your decoder. I think one example you didn't mention was bias noise.
Yes,
You can try to design your hardware to bias the noise and improve your decoding outcomes that way.
And converting things like leakage errors into erasures, if this is possible at the physical level. I mean, and a lot more interaction, I think, between experimental teams that are looking at the the properties of the physics of the devices and how they tend to leave the qubit manifold. I think are all important as well. I'm curious if I mean, this seems like a challenging practical problem in some systems, at least, to deal with these so-called leakage errors where the qubit leaves the 0-1 manifold. And I'm curious if anyone has any comments on how this interacts with error correction.
No, but I will, just say one thing, that if Barney and I were designing a classical communication system, we wouldn't try and make Gaussian noise, right? Because Gaussian noise has no corners. There's nothing to take advantage of. We would really like to have noise that's skew. And so this uniform Pauli error model isn't something that's giving us much to sink our teeth into. So if you can make a different model, then maybe you can take advantage.
Yeah, I mean, realistic systems have very non-uniform error distributions, and yeah, these are all things that we can learn from the experiments we're doing today.
Or
So one thing that I learned in my career, sorry.
I was just going to say a small thing, also, if you can, for like leakage, if you can fight them at the physical level, then that's also great too. Luckily for ions, you can potentially do leakage repumping, which is great. So it's important to identify your noise and see where you can, knock it out if you can.
So one thing that I learned in my career, I work with different systems, magnetic recording and flash memories and optical communications. And typically as coding people, we interact with the physicists who understand the medium very well, or the channel very well. So we typically run simple experiments with, binary symmetric channel, Gaussian noise, which are kind of the worst case scenario. And typically we kind of design some codes. And when you talk with engineers in companies, they will know exactly, if this code is applied into, more realistic setting, what kind of loss or benefits it will give. But then it is more interesting to, to learn from them, as Rob said, about these particular noise models, and incorporate this also into coding. So there is this also wide concept of coded modulation that, so for example, this GKP concatenation with error correction code is very, for classical people, it is almost like coded modulation. So you have some kind of analog encoding into some space, and then after that outer code is your, just ordinary, I don't know, LDPC code or some discrete code. And the crosstalk correlations and all this, we know how to do in classical. We still don't understand, at least I still don't understand these quantum mechanisms. And I guess with interactions with physicists and quantum people, we can learn this as well.
Yeah, so an area of opportunity there. Yeah, so more generally, right? So we have all of these techniques for addressing noise that we've kind of, I mean, at least over recent times, sort of worked on them independently. Device engineering, control, mitigation, correction, fault tolerant design, and we tend to work like these aren't really islands, and they interact with each other very strongly. And so it seems really key to encourage these kinds of collaborations. So I'm wondering what other areas of opportunity there are to look for these interactions, or maybe some obstacles we're not aware of to doing that. So I think you highlighted one of them, which is that we need a better understanding of the noise in our systems. This is something that we're learning from the noisy devices that we have today.
I mean, it's useful to interact with computer scientists in general. Well, yeah, anyone outside of our normal field, because like, from what I understand, how to do minimum weight perfect matching wasn't understood until like someone talked to a computer scientist. It's like, oh yeah, that's been solved for a long time. And we also need to like speed up these decoders and whatnot. So interaction with the computer scientists on how to do that, because we're just physicists just dumbly coding is really useful. But yeah, all sorts of domains, like it's useful to have communications, because there's, I mean, obviously from like the classical coding theory or how the actual physics and the hardware works, it's really important to utilize all that knowledge. See, because qubits are inherently noisy, and it's really annoying.
It is interesting. Lately, there has been several papers by big companies like Google and Microsoft, IBM, where they talk about hardware requirements or I don't know, these throughput requirements for decoders, for error correction. So, of course, they depend strongly on the platform, on kind of qubits that they use, but as engineers, it would be good to have some kind of a specification. Imagine that we have a customer, let's say Microsoft, and they tell us, okay, here is what you can do on your qubits, and we need this throughput for decoding, and we are going to put this in the refrigerator, and you cannot have more than that power consumption. This would then, I don't know, somehow guide the design and choice of codes. And we have experience with this. But this requirement, I don't know, it's kind of this target is a moving target, and things are improving and changing. But, it is hard to find from literature kind of exact specification of what we need.
I think like at least the quantum error correction community is slowly moving out of theory land and starting to realize some of these things, because like recent conferences, this has been a major theme, is like bandwidth, throughput, whether how many CPUs, how much power do you need to run these? Do you need a fusion reactor? And so on. So I think the community is starting to take notice of these things. So I imagine there'll be more information about that in the future. Although it's kind of hard to do, because like we don't really know what the future large-scale quantum devices will look like. Maybe we can, like with some good LTPC code, really shrink down the resources in it. But it is good to start talking about targets and doing resource estimation.
I mean, to some extent, you want to go the other way as well, and say, as theorists, if we had this additional connectivity, which maybe they can build, or maybe it's within the realm of possibility, then we could get some X amount of improvement.
typically when you build these big systems, you make a roadmap and then you kind of see who can contribute, which area can contribute by what, and see if you can make it. So we can, provide, some advantages in one area and maybe have some little bit leeway in other area. So some things are more difficult to do than others. And this communication and interaction kind of teaches us what is possible, what is difficult.
Yeah, actually, I mean, one of the things that you learn from communication is that if you want to get a certain error rate performance, and you want to get there with one technique, it's going to be really, really complicated. What you want to do is you want to identify 3 techniques that are complementary and do a little bit with each of them. So for example, when you communicate over a Gaussian channel, you do coding and shaping. And the combination of the 2 is manageable complexity.
So I think we have about 5 minutes left. So I wanted to give everyone a chance to make any closing comments that we haven't had a chance to talk about through the questions. So I just welcome you to use the remaining time to make any points that you didn't get a chance to say.
My dog is barking, so I will have a short. I will just thank you again for inviting us to this panel and the workshop. I learned a lot, and I think hopefully these interactions will also help us to collaborate more, and maybe also, I don't know, encourage NSF to change the maybe even the funding structure to build some of the system. One thing that we are noticing, NSF gives bursts of money, and we need to spend them quickly. And educating students that are both expert in error corrections and in quantum mechanics is not an easy. It is not a short period. So we need somehow a little longer time and some buffer to achieve this.
Yeah, that's a good point. I really worry about the amount of students that's going to be available for doing quantum error correction, as well as people who know a bit of quantum error correction and maybe are more in some other field like computer science or hardware or whatever. So anything that the field can do to encourage students, would be really great. And as well as as talked about previously, more communication between the different subfields, of course, is really important because we learn a lot. And it's really going to be exciting. It's going to be exciting seeing this field mature because things feel like they're getting realer and realer. Whenever I was a grad student, it didn't seem like we were going to have, I don't know, a single logical qubit in, I don't know, 20, 30 years. But now, the rate at which these things are taking off is really awesome. So it'll be an exciting ride to see what happens in the next 10, 20 years.